Good morning and welcome to our session where we are going to speak with you about scaling machine learning with containers. But what exactly means scaling? Scaling, it means like you have 10 of thousands training jobs monthly or 10 millions of predictions, and your research takes not only weeks, it takes only just like 1 day or maybe less. It's what exactly we are going to talk today with you. And my name is Victor, I'm developer advocate, and it will not be like, a theoretical session. It will be lesson learned. For that reason, today I'm not alone on the stage. My co-speaker, Rustem, and Rustem is not like regular customer. Rustem is AWS hero in ML specialization. And we will share his own lesson learned from his company. And Rustem?
Thank you very much, Victor, for the intro. Happy to present for you today. And basically, I want to tell a story how we migrated from just cluster solution to container solution, what were the challenges that we had, and how we were able to address them, what were the benefits, and what were the lessons we learned. So I will start by sharing a couple of words about what instrumental is. Then I will share basically what's the standard ML project lifecycle for any ML team out there. And then we will go over container solutions on AWS, then how we applied them during our migration, and then what were the lessons that we learned. And finally, we will have a demo which will showcase how the challenges can be addressed with container solutions. So let me start with instrumental. Basically, instrumental is a manufacturing optimization platform. It is used by a number of big customer brands. We have more than 4 billion data points on our platform and more than 10 countries where we are present. Customers utilize instrumental to find failures on their manufacturing line and optimize them at scale. How do they do that? With AI. They utilize our platform to use AI for tasks like finding unknown defects, things like missing components or incorrectly applied glue. Then for these defects, they can train monitors which will detect only specific defects and only them. And finally, they can drive corrective actions by deploying these monitors on their lines to find defects earlier in the manufacturing process. What does it mean in terms of requirements for ML at instrumental? That means that we have to be able to train and run predictions at scale. Basically, the numbers which Victor shared, that's something we need to achieve to make sure we can work with big customers out there. Next, models have to be flexible. It's just impossible to have a single model which can find defects for all customers. We have to adjust models for each individual customers and projects. And finally, models have to be robust. Because models are running on the line, it means that any issues with prediction pipeline on the edge will result in line stop, and we don't want that. So models have to be able to handle edge cases well. How does it transform into ML architecture? So first of all, training pipeline is in production with instrumental. That means that models can be trained based on user demand or based on data shift. And there is no engineering involvement when model is trained. Next, we have in-house solution for ML orchestrator. For things like model registry, storing predictions, retraining the models, everything is handled by instrumental, just because we have to handle it at scale. And finally, instrumental works with both image and non-image data. But for ML models, image is the primary source of data. So now that I shared a bit about instrumental, let's take a look at the standard ML project lifecycle. Let's say you got a request that you need to solve a pretty standard problem, quality control in industrial manufacturing. What are the challenges there? First of all, you need to be able to handle high variety of products and defects. Things like missing, for example, on the connector, as you can see on the slide, you may have multiple failure modes. So you need to be able to detect all of them. And sometimes you have borderline defects, like with foam on the slide. where like if it moves a little bit, it's not a defect. But if it moves significantly, that's a defect. And you need to be able to train from just a couple of images. Customers cannot wait for 10,000 images to pass the line before they can train the model. And finally, you need to be able to handle scale in both meanings of this word. When you get 10,000 units daily, you need to be able to handle that. And when you're running on the line, you need to be able to make sure that your models are fast, so you're not slowing down the customer production line. So what would be the steps here? First steps, like pretty standard research. We need to gather training data and label it. So let's say we gathered some training data, we labeled it. What do we do next? We have some baseline solution. So we're using some deep learning model, and we get baseline performance. And then we start iterating on different approaches, ideas, and improvements. So basically, we want to try as many ideas as possible. Performance doesn't increase linearly with the amount of ideas you tried. But the more ideas you can try, the better performance you can get. And let's say we arrived to like the best performing, like we tried a couple of ideas, we found the best performing one. Is the end of the story? No, it's just the beginning. Now it's the most interesting part, productization. So now, in addition to training part of the pipeline, which we already need to productize and make sure it adheres to production requirements, we need to add steps prior to that about data, preparing data for training and make sure it's correct. And then after that, we also need to evaluate and validate the model to make sure it's robust and will handle edge cases, because it needs to be able to run on the line. After that, we can follow standard software engineering practices for releasing this training pipeline to production. We basically want to package it, run tests, release to stage, test end-to-end, then release to production, do end-to-end testing there, then do staged rollout to a couple of customers, then to all customers. And now, the most interesting part. OK, we have our model running in production. So let's say customer decided to train a model to detect defects with thermal pad. They labeled data, model was trained, it runs predictions, it was deployed to prediction service, and now this curved thermal pad comes in, and model says, it's good. So why did it happen? Maybe there is an issue with labels in training data set. Maybe there is an issue with training code or model validation, or maybe there is discrepancy between training and prediction service. Let's say some library changed. Anything could happen. And to troubleshoot the process successfully, you want to make sure you can isolate each individual step to make sure it works. So now that we handle productization, comes the more interesting part, scaling. So let me pass mic to Victor.
Yeah, finally we enter production. So what does this mean? It means like we are done, we are happy, that we can finish our project and that's it. Not. In reality, it's not. Why? Because we need to scale. So for example, our applications, they more and more popular, and currently we need to run multiple jobs, like not one jobs per day, 10,000, million, thousand, and so on. We have to scale. But when we scale, also it's bring to us additional challenges. What I mean? If you have a couple of jobs currently running, what you can do? You can log in, for example, through the SSH to your container where you run your job and make some troubleshooting, just like review the logs, get some metrics, and so on. But if you scale in thousands or millions of jobs, you will need another solution to aggregate everything in one place and to have centralized system which help you to understand what's going on with your jobs. And of course, at some period of time, like as we have growing of our popularity, it means our cloud bill is also growing. So infrastructure is not cheap. And maybe someday our financial management will come to us and say, hey, what's our plan to cut the bill of AWS infrastructure? So we have to be aware about that and apply different practices, which we'll review a little bit later. But if we summarize of what the challenges ML team regularly have. So there are three main challenges. The first one is speed of research. You have your idea, and you need to verify your idea, to run these training jobs and see what's the results. Maybe you need to optimize on predictions. Maybe you're working on some other metrics, and you have multiple different ideas. If your research takes like weeks or months, so most probably you will move very slowly. But if you can do it like a couple times in a day, much better. Going to the production. So running on training, it's one of the way, but when you go to production, it's absolutely another approach, because now you have to be aware of what's going on in the production, how you can troubleshoot, and manage all of these jobs at the same time. And of course, it's scaling. So as soon as we get more traffic, like we have more clients, we need to be ready to scale, and scale in the right way. So I mean, like, not only from troubleshooting perspective, but also from optimization, cost optimization. But how containers can help us in these situations? So that our talks is like scaling ML jobs using the containers. So first of all, why containers? If we look at traditional microservice applications, everyone currently, most of the people use containers because it's easy to set up, run, and so on. But what about ML? ML has some specific requirements. When I said specific requirements, I mean you will need some drivers, for example, to run your jobs, some frameworks, and so on. And containers can help you to solve it. So what's the key benefits from containers? I would say like we have a couple of them. The first, like portability and consistency. So containers can help us to solve the problem that was works on my machine, like my laptop. It will work also on production, in my research environment, in production with the customer, the clients, and so on. Scalability. So if we run everything in the containers, and industry currently knows how to scale containers using Kubernetes, using other systems, so we can easily and quickly to scale our system. Isolation. When we put everything in our container, like our dependencies of libraries, dependency for our jobs and so on, we put it together and we isolate it. We don't need to add additional requirements. And reproducibility. So it means like if you run in your research environment or some another environment, you can reproduce the same on production, or for example, if you got an error on production, you can repeat the same on your lower environment. But what kind of the services in AWS we can use to run our containers? I would say we can split them like in three main areas. The first one, it's I would say more traditional. It's managed containers, Kubernetes, EKS, ECS, AWS Batch. So in usual, like you need to run this infrastructure by yourself, to run Kubernetes cluster, manage your updates, and so on, so on. So it's the first approach. So it sounds like we have to do a lot of operations, because like to support Kubernetes clusters, sometimes it's not easiest task. The second option, it's serverless containers. In this situation, just like AWS Fargate or SageMaker jobs, you will be responsible only for your containers. And when you need to run something, AWS will provide whole infrastructure what you need. EC2 instance will be provisioned as soon as you run your job, not before, like for example in the Kubernetes cluster. The last one is serverless functions. So there is like you're only responsible for your containers, like for zip package or Docker image, where you manage your containers, and that everything else will be on AWS side. But what about hardware? Which hardware will be best for me, and what kind of options do we have in AWS? You know, like in AWS, we have multiple options, as you can see, based on the different type of the services to run your containers. Also, it's related to hardware. So if you prefer to use classical NVIDIA chips, so your options will be P instances, P3, P5. If you like listened yesterday announcement from Matt Garman, you know like we have our own chips, Trainium, Inferentia. Highly recommend to look at these chips because it will be cheaper compared to traditional. Also, if you have some specific jobs and you need some third-party chips, like for example instances with Dell, so you can do it. Again, dependent on your needs, depending what kind of the jobs you run on in your machine learning environment. Okay, if we compare, for example, SageMaker training jobs and classical workflow, I mean like classical, it's running our own containers. So I would say we can compare it in three different ways. So the first one is operations. If you run your own Kubernetes cluster, you have to be responsible for this Kubernetes cluster. You need to run all of this infrastructure, make some updates, upgrades, make sure that all of security patches inside in your environment, and so on. In case in SageMaker, you just don't need to do it at all. Scalability. In SageMaker, just like you will be limited only on your AWS account limits. Rustam later will explain what exactly means and when you need to do to make sure that you have enough capacity to run your ML jobs. And the last one is observability. If you're familiar with continuous worlds, you know like what is sidecar, and sometimes if you need to monitor something to understand what's going on, we have to install sidecar containers to get some logs, metrics, and so on. So it's your part if you run like classical workflow. In SageMaker, out of the box, it provides for you this information's metrics like CPU, GPU, memory, your custom metrics, which we will see during our demo. And also have very great integration in SageMaker with SageMaker ecosystem. If you need to adjust hyperparameters, you can do it very easy. But I also mentioned that you can use serverless at all, and we see more and more popularity to run ML jobs inside in Lambda functions. So quick refresh, what exactly Lambda function and what exactly Lambda is. So first of all, Lambda provide for you possibility to like scale in super fast way. So if you have like 0 now and just like in a few seconds 1,000 of the jobs, you can do it with the Lambda function. So it's extremely scalable. Another one, it has very good integration with another services. Like for example, if your scaling like is too high and you need to proceed a little bit slowly, for example, you can integrate with SQS. Of course, it will be cost higher compared to traditional EC2 instances per millisecond of compute. Yeah, but in general, as we don't use idle, I mean, like as soon as we finish with our job, we don't pay for that. So in this situation, we will see maybe cost benefits from that. Another point, it's related to the cold start. When we run our Lambda functions, it will also require some time to prepare our functions. But what exactly it means? Like, if you look at this diagram, you see we have like AWS responsibility and as usual customer responsibility or user responsibility. So in AWS side, we have download code, container setup. In your side, like in the customer side, you need to prepare, initialize your runtime, like a code, and it's only after that to run the code. But if we try to reflect this cold start to ML jobs, how it will be affected, like what's exactly happening under the hood. So download codes. So we need to download our image. It can be Docker image, or maybe you put everything in your zip archive, for example, in Python. You need to set up your container, like OSI or in general, like runtime. Initialize your runtime, which means like download all of the libraries, models, all of the stuff. And only after that, you will be able to run your job. From one perspective, it sounds like we can do something, yeah? And a good solution here it will be snap start. What exactly snap start is? So we will make a snapshot, like we have this cold start with multiple steps, like download code, initialize runtime, and so on, and make a snapshot in this period of time when we initialize everything, and our container, our runtime is ready to proceed with request. So we will make it this snapshot, and the next time when you will need to run the same Lambda function, we will start from this point. So we will not waste a time, and this cold start will be reduced dramatically. And I have very good news, especially if you from ML world. Just 1 week before reInvent, we announced support new languages, .NET, I think not for you, but Python. It's a very good option because I know many ML engineers use Python to write their ML jobs. So very, very great news. But we discussed these containers, we discussed serverless, scalability and so on, but how to migrate real productions to this ecosystem?
Thank you, Victor, for sharing different container options. So now, yes, let me tell you a story like how we did the migration using the container options outlined by Victor. So our starting point, pretty standard for a lot of machine learning teams out there. Research cluster, just research machine basically, where we would run some experiments, and single production cluster where we would run training jobs and prediction jobs. And basically, it would be invoked by production backend orchestrator, and the results would be written to SQS. What are the challenges with that? Basically, for research environment, we had steep learning curve. For new hires, it was hard to start running new experiments. And also, there was a big gap between research and production. Libraries in research and libraries in production were different versions, and that was causing a lot of issues. And for production, there were challenges with handling peak loads because it's a cluster. And it was hard to troubleshoot training jobs because basically clusters runs multiple jobs. So it's hard to isolate and understand what went wrong. Migration itself sounds pretty simple. Like, we moved all predictions to Lambda, and training jobs in both production and research, we moved to SageMaker training jobs. So pretty straightforward. Now let's take a look at how it actually works in architecture. So for our research, in case someone wants to run a new experiment, they make changes in the code they committed to Git repo. CI process then publishes new container image to ECR. And then someone, data scientist or ML engineer, they can use Research Orchestrator to run this new container image using SageMaker training jobs in parallel, and then aggregate the results. So how does it look like in terms of trying different ideas? Actually, it's pretty simple. Like, every time you try new ideas, you can create new branch, you push changes, you get new container image for each commit, and you can check that you get better performance for new container image version. And every time you merge branches, even like to research branch or to main branch, you can verify that there was no regression, that basically any changes which was happening in the main during your research didn't affect your idea, your workflow. Now let's take a look at production architecture. Looks very similar to research. That's the idea. We're still using SageMaker training jobs, but this time around, it's not invoked by research framework. It is invoked by Lambda, which reads from SQS, and then basically getting messages from backend orchestrator. Other than that, pretty straightforward, just different repo like production repo for container images, and same training jobs. So you can see that even on architecture-wise, it's similar to research, and there is not a lot of gap even in terms of like changing infrastructure to release something to production. For prediction, it's even more simpler. So yeah, same container image just for Lambda. Lambda references this container image. In case we want to deploy new changes, we need to run infrastructure update for this Lambda. And yeah, Lambda reads from SKS, Lambda writes to SKS, standard pattern. Like, there are obviously the other queues hidden there, but that's like the gist of it. So this new architecture, how did it help with the challenges which we outlined previously? First, speed of research. With speed of research, it became pretty fast because now we are flexible. We can try different instance types. We can introduce new libraries. In case we can run multiple Docker images in production. So we are not limited by specific dependencies. We can try different ideas very easily. Time to run experiments also became significantly faster. Now, instead of running research sequentially, we can run it in parallel. And iterations are taking hours instead of days. And it's very easy to learn. For people who just joined the company, they can start running experiments from day one. They don't need to figure out how research framework works. They just need to commit the change, and then they can run the new container image. So how does it look like? Basically, if you need to run like experiments sequentially on the one single server, like that can take a lot of time. With container image, you get additional latency because now you have like CI step. But after that, if you can parallelize your research experiment job, you can run it in parallel, and you can get pretty good improvement in terms of iteration speed. So what were the lessons we learned during this process for research framework? Tooling is extremely important. You want to make sure that A, you can run end-to-end workflow locally, so you can catch bugs early before you run actual experiment. Next, your CI pipeline needs to be able to publish container images fast. It shouldn't take an hour to publish container image. It should take like 5 to 10 minutes, which can be achieved with certain optimizations like container layer caching. And finally, your research framework needs to handle parallel experiments. Otherwise, you won't be able to get benefits of speeding up your iterations. And handling parallel jobs is not just about starting the jobs. It's also about restarting failed jobs, retrying them, and be able to aggregate the results. So next, productization. How did new architecture help us with productization portion? Basically, now time to production became significantly lower because it's easier to productize. We basically have very similar infrastructure. And gap became significantly smaller because we know that the problem is never in lower part of the stack because it's effectively the same. And every time we have an issue in production, we can always take production image in research and inspect if there was any regression there. That helps to isolate the problem and understand whether it was like in libraries code or outside of the ML workflow. And finally, a bit of even a process change, I would say. It makes it easier for ML team to manage production because it's the same service and the same tooling they're using in research environment they can use in production environment. And that both speeds up investigations and also reduces pressure on machine learning team. Here you can see how the usual SageMaker training job page looks like in AWS console. We will show more details during demo. On high level, here you can see that all parameters like container image version, like metrics and logs are available on this page. In terms of features, the important part here is that every training job you can clone and change any parameter. That means that you can clone it and start investigating like what the parameter could be the root cause. And finally, using AWS project SSH SageMaker helper, you can SSH into your cloned job in case you need to run something locally within the job itself. So to isolate the problem further. So yeah, sorry, we will take questions at the end, sorry. Yeah, so what were the lessons learned here? You want to make it flexible to support multiple container images. This way you can get benefits of flexibility. Because now you have separated training and inference pipelines, you want to ensure that your models are backward compatible. And the best way to do so is to have inference frameworks like Onyx or similar. And finally, a bit of a serverless practice. You want to make sure that AWS infrastructure is part of your DFCI process. So for example, running Lambda, so SageMaker training jobs, simple jobs, basically simple smoke tests you can use to find issues earlier before stage or God forbid production. And finally, how were we able to address the scaling challenges? Pretty simple. As Victor shared before, with SageMaker and Lambda, you just increase limits, that's it. That gets you, I would say, 90% of the way. Like the last 10%, if like your limits are significantly high, you start like hitting specific limits, but that means that you hit a very large scale. So for a lot of cases, you will be covered by just increasing limits, but that has to be done in advance. Second, cost optimization. SageMaker training jobs provides a lot of low-hanging fruit for optimizing costs, as I will share in the later slides. And finally, when we need to share ownership of ML pipeline with other teams, it becomes easier because now we can generate CloudWatch metrics, and based on these CloudWatch metrics, we can generate like alerts and dashboards, which can be used by, let's say, SRE team to understand what's happening wrong with ML pipeline. To quote Dr. Manuel Vogels, cost optimization is incremental. It's impossible to optimize in advance, and you want to make sure, like, an optimization is an ongoing journey. So you want to make sure that your infrastructure is flexible so you can apply different optimization techniques. What does it mean for SageMaker training jobs? There's some low-hanging fruit you can try. For example, right-sizing instance based on your training job. Sounds very straightforward? It is. Basically, if you have small data sets, you don't need large instance, and if you have large data set, yes, you need to use large instance. You can switch to a different instance type. Remember, like, we made it very flexible to switch to different instance types. That means that you can try different ideas in research, try different instances, and if you see that there is a price-performance benefit, you can switch very easily. You just change one parameter, and you can both test it in the research, verify that there is no regression, and then easily flip it in production. And finally, you can use spot instances. We will show during demo how it works, But in short, that can give you a lot of benefit right away with changing just one parameter. But you want to keep in mind that your code has to be able to work with interrupts, which can happen with spot instances. A bit more complex approaches, if you need to optimize the cost further, you can start switching to different services. Because now you have event-driven architecture. That means that you can change compute services. For example, you can replace SageMaker training jobs with AWS batch, which will give you some improvement in terms of performance, but it will increase operational complexity. Or you can replace Lambda with SageMaker asynchronous batch inference, which again will decrease the cost, but the max available throughput may be hurt. And finally, you can utilize AWS savings plans in case you have predictable workload month to month, so you can pay it in advance. So what were the lessons learned here? Basically, you want to make sure it's easy for you to change instance type in production. You want to be flexible in case you want to do any changes. Increasing limits is simple. You just need to open support case. But it has to be done in advance because it can take a couple of days to be increased. So you want to make sure you have right alerts and metrics in place to understand when you start hitting resource utilization limits. And finally, to handle peak loads of inference and training jobs, you need to have a separate observability tools. Basically, like you want to make sure you have alerts and metrics and dashboards to be able to handle like thousands of training jobs and millions of predictions. So now, would be happy to pass mic to Victor, and Victor will show like our awesome demo.
Yeah, so we are going to my favorite part because I'm the person who prefers not only to speak in but also to show something. Demo. So what we will do during the demo? So it will include three main different scenarios. We will try to set up our infrastructure almost from the scratch to show how you can do some adjustment, your experiments, for example. We will try to troubleshoot some of the jobs is going to fail. Also, we will try to scale to see how spot instances can help us to save money. I think you will see like 90% almost. It's a little bit spoiler, but anyway. And the last one, how much it will take to you to make your experiment. So it's pre-recording demo. I think you will understand why, because it takes some time to make, run the jobs and so on. So what's the data set we use? It's official Amazon data set, which is called Visa. It's included only good, it's included good and bad images. As you can see, we have 12 subset. And also during the training, we will have only good some images, but during our execution, just like to verify is it good or not good, we will have both like good and bad. Also, we will use autoencoder. I believe if you're familiar with ML, you know, like, so in general, as we use only good images, we will try to decode and encode our images to make predictions for the next one. So where we store our code, it's Code Catalyst. In Code Catalyst, you can create your own project. That's what I did. That's where we store our code. What's inside in our code? Like, what the files do we have? We have a train file where we described our training job. Also, we have requirements as usual, and as we run everything in containers, we need a Docker file. So in the Docker file where we prepared everything for our container, like to use the right Docker images with frameworks, with drivers, and so on. And the last file is Python script. This Python script I'm going to use to run my jobs, like one job or multiple jobs. You know, like I figure out that in my training file, we used old optimizer, not very good optimizer, I would say. It's RMS optimizer. And let's change this to Adam optimizer. So as you can see, I try to type optimizer, like Optim Adam, and Amazon Q, generative AI, almost everywhere, help me to finish this line. So I just like it super quickly to finish it, and it's going to commit my changes. As I already mentioned, we store everything in Code Catalyst. And Code Catalyst is not only your source code, like a Git repository, but also provide for you capability to run CI/CD workflow. This is where we are going currently. It's our CI/CD workflow. And our process, like our job, is currently in running status. And as you can see currently, we have not only to build our Docker image, we also create a container registry. Why? Because when I create this project, I use blueprints from Code Catalyst. It helped me to save a lot of time, and I can quickly and easy to set up my environment. So, and here we go, this is where I use some magic of editing the video. So, I mean, like I speed up a little bit the process because it took around 10 minutes to build my container and publish to my container registry. Let's double check. So, as you can see, Docker tag. So, sounds like I tag my image and push it to container registry. Let's switch to container registry and double check that we have this image in our container registry. And here we go, this is my image, which I currently built a couple days ago. And most important part here, this is image almost 5 gigabytes. So it's very important when you run your image. So it's a time to run my job. So I finish with changes for optimizer, and let's run our first job. For the first run of my job, I'm going to run only one job to see how it looks like from SageMaker training job perspective, and in general what I can see inside in my job. So I currently go into Amazon SageMaker training jobs, and we'll see my job currently in progress. Again, just like for demo purpose, I just speed up a little bit the process because in general it takes around 10, maybe 20 minutes depending on availability resources and so on. So it took for me 11 minutes. Let's look inside in the job what we can find as results. So first of all, how much time we spent with EC2 instances. This means we will pay for these seconds. Our training image is our Docker image. So for example, if you have multiple, you can figure out which one. What's the type of the instance we use for this training job? Where is located my data set? I have some metrics, like my custom metrics, we'll discuss a little bit later. Also, I have my hyperparameters, where I can understand, I run this job with these hyperparameters. Also, I have multiple metrics like CPU utilization, GPU utilizations, and so on. And also my custom metrics as loss and ROC-AOC. Also, if we need to go deeper, for example, for this specific job, we can go to logs to double check that everything works fine as we expected. And if we scan currently this output from this job, for me it sounds good because losses go into 0, and so finally I have the metrics of ROC-AOC. Okay, if we scroll a little bit down, we will see our archive. This is a model which we can use in production if we're happy with the result. So in general, when you work with ML jobs and when you prefer to set up your environment, so CI/CDs can be very good options. So my options was Code Catalyst, highly recommend. Why? Because it's a very good integration with AWS system, and it will be very quickly too easy to start. Because if you need to store a code, so you can do it. If you need to run, for example, to store your artifacts, Code Catalyst have very good integration with AWS. So in general, what I'm currently doing, again, is to show the Docker file. That's what we have. And in SageMaker, when we run our job, what's most important for us is we can troubleshoot our job. So, for example, if we have some issue, for example, during the running of the jobs, it's failed, and we can go to specific of the jobs. So currently, I run only one job. It sounds super easy. This is what I described when the scaling we need. For example, if you have only one job, it's super easy because you can troubleshoot and see what's going on. But if you have thousands or millions of the jobs, especially if you have productions with a million jobs, then need to back to the resource environment. So you need to have very good system to centralize your monitoring, logging, to have a good observability system to understand what's going on with the system. And SageMaker can be very good options because it's collected for you all of the metrics. And in the case if you have some issue with some jobs, you can go deeper and rerun it, for example, to clone the job, to troubleshoot what's going on inside, make some adjustment, make some experiments with specific of the jobs, with specific container, with specific environment, hyperparameters, and so on. Again, we're back to Code Catalyst, almost done to our previous state. So when we build and send it to our Docker image, my recommendation also we didn't mention, but I think it will be very important to highlight it again, especially in Lambda functions. If you can make smaller of your image, you will save the time during the cold start in the Lambda, and also, anyway, you will save the time because it will not require to download so many files like with your model. In our case, you can see currently it's almost 5 gigabytes. It's I would say pretty okay, but if you can do it less, highly recommend to pay attention on that, because it's one of the way how you can make optimization, not only from the size, but also from the price perspective when you run your job also. Here we go. This is how I use it to run. So you see, like it's a Python script, just start one job. And switching to SageMaker console. So in SageMaker console, well, what we will see, it's my training job, training job, and the current state is active, like it means like in a progress, we're running. Again, as already mentioned, we use a little bit a magic of video editing. I mean, I cut it down this process just like to save time during our presentation. So it's completed, and we can see everything what's happened inside in this job. Many different metrics. One of the most important, like from the cost perspective, it's how much time it took for me to run this job. When we will run on the spot instances, we will see how much money we can save in spot instance. My data set, sometimes it can be very important because you identify what the data you use for this training job. Your parameters. So in our case, as you can see, we defined some our custom parameters based on the output of our job. It's loss and rock you see. Also like standard parameters, I mean standard metrics like CPU, GPU utilizations, and so on. The logs is very important because in the log, that's where you will start, most probably where you will start your troubleshooting process. And in these single jobs, it looks everything is good because we don't have any errors. And for example, loss for us as our custom metric is going to the 0, and we have at the end rock AUC as a metric. Also, if we scroll down, we will see the archive with our model. This archive we can use in the future in the production. And we finally back to my previous run. So what I see in this graphic, very low utilizations of GPU, only 15%. For me, it sounds like I paid too much money for nothing to AWS, and I can improve it. So how I can do it? So in my hyperparameter, I'm going to change from 100 to 512 parameter, and I think it will help me to change this GPU utilization. And in this time, I'm going to run not one job, 100 jobs. But if you remember, my data set has only 12 data sets, like 12 different data sets. But we decided for demo reason, just like to split it and run multiple times on the same data set. Also, I run these 100 jobs on spot instances. Again, just like to save money, to save the final number for my bill. And here we go. I run almost all of them and ready to back to SageMaker training job. So let's a little bit adjust of UI to show all of the jobs what we currently have in a progress state. And again, like a little bit speed up this process because it took around 10 minutes to show that we're done with all of the jobs. So let's scroll in and let's see all of the jobs. It's in the green state, like it's a good or failed. Oh, I have some of the jobs, it's failed status. So it's a good time to troubleshoot one of my job. So you see, like I run 100 and some of them is failed. What can be the reason? What's happened? So my process of troubleshooting to start with logs. Let's go to the logs of this job and see what's exactly what's the root cause, what's the error. As you can see, it's we don't have some file. Sounds like we defined the wrong data set, and I think we can rerun this job. So for me, it sounds like I have PCB failed as data source. It's a wrong data source. Of course, what we can do, we can clone this job. When we clone the job, we completely clone this absolutely the same what we have previously. But now we can make adjustments, like for example, to change. I don't know, like EC2 instance, maybe our Docker image, maybe my hyperparameters, or as in my case, as I figure out that the root issue of this problem, it's data set. So I'm going to change from PCB file to PCB1.
And this dataset should be okay because I'm 100% sure that we have this dataset inside in my S3 bucket. So let's save these changes, and as soon as you save the changes, this job is going to rerun, like to run the copy of these jobs with your new parameters, like with my new dataset with PCB1. And it's finished. Sounds like it's green, it's okay. Let's check inside in this job. We see absolutely the same parameters like metrics and so on. And based on the metrics like raw accuracy and loss, I understand it's finished, is on the good way. So this job is done. So we figure out what's the root cause of our failed job. But if you remember, we run these 100 jobs to show you, first of all, how much we save using the spot instances. And in my case, it's 90%. Amazing numbers. So like count for the whole jobs, almost 400 seconds, but I will go into pay only for 40 seconds. And also I increase the number of GPU utilization memory. Currently it's 48%. Better compared to the previous. Previously when we run it was only 15%. Okay, but I have another metrics, it's our custom metrics, raw AUC, and I can get this metrics only from in SageMaker only from one jobs. But what if I try to combine all of them in one place? So I can do it my Python script. It will collect all of these metrics from these jobs. For that reason, I use suffix. Suffix will help me to filter all of my jobs. And here we go, I got this raw AUC metrics aggregated across all of my 100 jobs. We see this number, but you know the main idea of this part of the demo to show you how we can quickly to make an experiment. So I understand maybe if I made a changes in my latent space, like for example these two specific numbers from 256 to 1024, maybe it will help me to adjust these metrics. I have this like as an idea and I want to do this experiment in my research environment. So as soon as I will finish with my changes, like my experiments, it's like super simple for demo reason, but I believe in your case in production you have much complex. I'm done with committing my changes and pushing to Git repository. How much it will take for me to see the results of this job. For that reason, I bring another clock on this screen just to show you how fast we can see the results from research, from our experiment in our research environment. Again, like the first step, we'll need to rerun again our CI/CD pipeline. So it means like we have to build again our Docker image. It took some time, like 12 minutes. As you can see, it's finished. And we're ready to rerun our jobs. In this time, I'm going to run again 100 jobs to repeat the same experiment like as previously, but not going to use spot instances. It will be on-demand instances. And here we go. Let's run it and see what will be the results. I run all of my jobs. It will take again a little bit of time to proceed with all of these jobs. But again, like magic of editing the video helped me to save our time. It took again like 12 minutes to run the job. Some of them it's failed, but it absolutely was happened previously. The main purpose of this demo to again collect of the raw AUC metrics and see what's the average data. And let's copy and back to my file where I store the previous result. And here we go. Let's look a little bit, zoom in and see, do we have the changes? For me, yes, we have a small changes, not dramatically, but our changes was not, you know, like so complex and so on. But previously it was 0.6. In our case, it's 0.6 and 2. It's increased these metrics. This is how we can quickly run our experiment in research environments. So we learned today a lot of, and I think it's a good time to make a summary and provide for you some takeaways from this presentation.
Thank you. Thank you, Victor, for the awesome demo. So yeah, what are the main takeaways from our presentation? Is, I would say on high level, make sure that you have good tooling, because good tooling is important if you want to run quick iterations. So that's one thing. Second thing is you want to make sure that your infrastructure is flexible, because you get a lot of advantages both from scalability, from like speed, and also cost optimization perspective. And third part, make sure that you have right metrics and alerts in place, because that helps to both scale things further and that helps with troubleshooting
your ML pipelines. In case you want to learn more about it, here are different links on this slide. So there is a good workshop on learning about SageMaker from idea to production. There is a SageMaker Sage Helper project, which I mentioned before, and two open source projects managed by me, Step Functions to Processing, which use different AWS compute for machine learning purposes, and Lambda Pax, which has different machine learning libraries optimized for AWS Lambda. So, and demo which we showed you today is actually in Step Functions to Processing GitHub repo. So, thank you very much for your time. Feel free to reach out to us through emails on the slide. We'd be happy to answer all of your questions, or through social links on LinkedIn on the slide as well.